Ashton Grossman, and this presentation is for Physics 2211, Lab 3 on black holes and orbital motion. In this lab, we'll analyze the motion of a star orbiting a black hole, and by applying Newton's laws of motion and the gravity to the star's trajectory, we can estimate the mass of the black hole causing the orbit. The goal of this lab is to determine the mass of a black hole using the observed motion of a star orbiting it. To do this, we use computational modeling to analyze the star's trajectory and calculate quantities like velocity, momentum, and the rate of change of momentum. Using Newton's second law and the gravitational force equation, we can determine the force acting on the star and estimate the mass of the black hole. This lab relies on several key physics principles. First off, momentum is defined as mass times velocity, or P equals mv. Second, Newton's second law states that the net force acting on the object equals the rate of change of its momentum, which is written as F net equals dp over dt. Finally, Newton's law of gravitation describes the gravitational force between two masses as g times the product of their masses divided by the square of the distance between them, and all these principles together allow us to analyze how gravity affects the motion of object in orbit. Momentum describes the motion of an object and depends on both its masses and velocity. When momentum changes over time, that change corresponds to a net force acting on the object. The force can also be separated into components. The component parallel to motion changes the speed of the object, while the perpendicular component changes the direction of motion. In orbital motion, this perpendicular component is what causes the object to follow a curved path. The star's motion in this system is caused by the gravitational attraction of the black hole. According to Newton's law of gravitation, all masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. In orbital systems, gravity acts as the centripetal force that continuously pulls the star towards the black hole, while the star's velocity carries it forward. To estimate the mass of the black hole, we combine Newton's law of gravity with Newton's second law. The gravitational force on the star depends on the mass of the black hole, the mass of the star, and their distance apart. By setting the gravitational force equal to the net force calculated from the change of momentum, we can solve for the mass of the black hole. This equation is evaluated repeatedly through the star's orbit to obtain many estimates of the black hole mass. In this analysis, the system is the star whose motion we are studying. The surroundings are the black hole that exerts the gravitational force on the star, and we assume that the black hole is the dominant source of gravity affecting the star's motion. The simulation uses several initial conditions. The star is a mass of 2 times 10 to the 30th kilograms. The time set between observations is 1 Earth day, or 86,400 seconds, and the black hole is located at the origin of the coordinate system, and the star's trajectory is generated uniquely using a seed based on my email. So now I'll explain how the computational model works. The program begins by calculating the velocity of the star using changes in its position between each time step. From this velocity, the program calculates the star's momentum using the equation P equals mvp equals mvp equals mv. Next, the change in momentum is calculated between two consecutive time steps. Dividing this change of momentum by the time interval gives the rate of change of momentum, which according to Newton's second law is equal to the net force acting on the star. This force is then separated into parallel and perpendicular components, so we can analyze how the force affects both the speed and the direction of the star's motion. After calculating the net force acting on the star, the program uses the gravitational force equation to estimate the mass of the black hole. The distance between the star and the black hole is calculated using the star's position vector. Using the magnitude of the net force in this distance, the code solves for the mass of the black hole using the rearranged gravitational force equation. This calculation is repeated for every time step along the orbit, producing many estimates of the black hole mass. So this slide shows the visualization produced by the simulation, and the orbit of the star is displayed along with vector arrows representing the net force and its components, and these arrows illustrate how gravity continuously acts on the star. The perpendicular component of the force redirects the star's velocity, which causes the star to move along the curved orbital path rather than a straight line. So the simulation calculates a mass estimate for the black hole at each time step along the star's orbit. Because the calculations involve numerical approximations, these values vary slightly from one step to the next. To obtain a single result, the program calculates the average of all the mass estimates. The average black hole calculated in this simulation is approximately 8.4451 times 10 to the 33rd kilograms. These results are consistent with the physics of orbital motion. The star remains in orbit because the gravitational force from the black hole continuously redirects its velocity. The perpendicular component of the force changes the direction of the star's motion while its velocity carries it forward, and this combination produces an elliptical orbital path around the black hole. So there are several possible sources of error, including numerical rounding and calculations, approximation velocity from discrete efficient measurements, and then finite time step resolution. And finally, the model assumes that the star is influenced only by the black hole and ignores any additional gravitational interactions. So in conclusion, this simulation demonstrates how Newtonian physics can be used to estimate the mass of astronomical objects. By analyzing the motion of a star and applying Newton's second law with the law of gravitation, we were able to estimate the mass of the black hole responsible for the orbit. This type of computational modeling is similar to methods used in real astrophysics research to study systems that cannot be observed directly. Thank you.